So the lesson today is going to be a reminder about geometric sequences, which I know you've done in year 9, and we've also kind of touched on it when we've done various things about exponential functions. So first of all, what is a geometric sequence? Well, if we start with some number a, and then we multiply it by r to get ar, and then again multiply by r to get ar squared and ar cubed and so on, this is a geometric sequence. So we have to multiply by the same thing each time. So r is called the common ratio. That's the multiplier, the thing you multiply by to get the next term. And a, of course, is the first term. And then the nth term, and if the terms are u1, u2, u3, and so on, the nth term is un. Un is going to be equal to a, and then what power of r do we need? Well, the power of r matching 3 is 2, and the power of r matching 2 is 1, so it's going to be ar to the n minus 1. So let's just see one or two examples. So first of all, consider the sequence 1, 3, 9, 27, 81. So here, well, a is the first term, that's 1, and r is the thing we're multiplying by each time, which is 3. So we get a, which is 1, so un is a, that's 1, times r, 3, to the n minus 1. Then obviously multiplying by 1 doesn't make a difference, so this is just 3 to the n minus 1. And if we take a second example, and here we want to find the next term and the nth term, and let's consider the sequence 5, 15, 45, 135, and so on. So now a is the first term, which is 5, and r is the thing we multiply by each time, which is 3. If you're ever unsure what r is, you could always divide two consecutive terms. We could do 15 divided by 5 to work out r. So that's another way you can work out r. But again, the nth term is 5a times 3 to the n minus 1. And the next term is, so u5, the fifth term, which is the next term, is going to be 135 times 3, which is 405, I think. Done. Okay, example 3. So now we want to find the next two terms and the nth term of the sequence root 2, 1 of the geometric sequence root 2, 1, 1 over root 2. So here we can see each time we're dividing by root 2 or multiplying by 1 over root 2, which is the same thing. So r is 1 over root 2, and a is the first term, which is root 2. So to get the next term, we're going to divide again by root 2, which would give us 1 over root 2 times root 2, or 1 over 2, a half. And the one after that, again, we'll divide by root 2, we'll get 1 over 2 root 2. So these are the next two terms here that I've just written down. And then the nth term is a times r to the n minus 1. So that's a little bit ugly the way it's written there. So let's try and write it maybe as a power of 2, which would be a bit nicer. So recall that root 2 is 2 to the half, and 1 over root 2, reciprocal is a negative power, so this is 2 to the minus a half to the n minus 1. And then we can multiply the powers here. So we have 2 to the half times 2 to the minus n minus 1 over 2. And then we're multiplying so we can add the powers, so we have 2 to the half minus n minus 1 over 2. And it simplifies just slightly further because it's now 2 to the all over 2, 1 minus n minus 1, which is the same as 2. And then we have 1 minus n plus 1, so that's 2 to the 2 minus n over 2. And that's it. So we can use the law of indices to simplify that. Let's look at one more example, which is an exam question. And it wasn't an easy question. I think it was at the end of the paper. The question was, if I remember correctly, root x minus 1, 1, and root x plus 1 are the first three terms of a geometric sequence. And the question was, find the value of x. Okay, so that looks pretty daunting. But firstly, note that r is the thing you multiply by. So clearly, to go from 1 to root x plus 1, we must have r is root x plus 1. So that's the only thing we can multiply 1 by to get root x plus 1. But also, well, in fact, that tells us, doesn't it, that the thing we would have had to multiply this by to make 1 is also root x plus 1. So we must have that root x minus 1 times root x plus 1 is the second term, 1. This is a, this is r, so this ar, that's the second term. Now let's expand the brackets. So we're going to get root x times root x is x. And then we've got minus 1 times 1 is minus 1, minus root x plus root x. So those are going to cancel, equals 1. So x minus 1 equals 1, so x is 2. And that's the answer. I think if you, so the thing I'm going to say next is really just if you're interested only. So you might want to stop now, but if you're still interested in learning more, then keep watching. So one of my favorite problems in maths is the following question. It's to simplify this infinite square root expression. And the number 2 isn't important. I can replace that with a different number. The question is, what is it equal to? And this ellipsis here means we keep going forever. So the question is, what is it equal to? And so I could write this. Well, root 2 is 2 to the half. And then I've got root of root 2. Well, root of root 2 is 2 to the half, which is 2 to the quarter. So I've got times 2 to the quarter, and then root of 2 is 2 to the 8th, and so on, 2 to the 16th, and we keep doing that forever. And then we're multiplying, so we can add all the powers together. And then the question is, what is a half plus a quarter plus an eighth plus a 16th? And I think I've showed you that before by illustration. If we start with a rectangle and we shade a half, and then we take a quarter, and then we take an eighth, and then we take a 16th, and then we take 1 over 32, and then 1 over 64, and then 1 over 128, and so on. And we keep adding them up, and they're getting closer and closer to the whole thing, which is 1. So this is nothing more than 2 to the 1, which is 2. However, what if we didn't have square root? What if we now had cube roots? What would be different? Well, we would get 2 to the 3rd plus a 9th plus a 27th, and so on. And you could ask, well, what is the sum of this? And now you can actually do a trick like I've just done. I might save the diagram for another time, but yeah, I did think of a diagram that illustrates what this sum is equal to. But notice that each of these numbers, well, they're terms in the geometric sequence, where a is a third and r is a third. So this is the sequence a third to the power n. Or if you prefer 1 over 3 to the n or 3 to the minus n. So we're actually adding up all the terms in this sequence. And in general, if you have a geometric sequence, AR squared, and so on, you could ask what happens if you add up all the terms. So we have this infinite sum. Ellipsis means we keep going forever. Let's call it S. And the question is, what is RS? Well, that's AR plus AR squared plus AR cubed plus AR to the 4, and so on. Now let's subtract these two things. So S minus RS, well, what cancels? Well, we've got AR minus AR squared minus AR squared, AR cubed minus AR cubed, AR to the 4 minus AR4, and so on. So everything cancels apart from this A here. So now let's factorize out S. So we have S brackets 1 minus R equals A, which tells us that S is A over 1 minus R. So that's really neat. So there we go, there's our answer. So if we want to work out this sum here quickly, 1/3 plus a 9th plus a 27th, A is a third, R is a third. So A over 1 minus R is a third over 1 minus a third, which is a third over 2/3, which is a half. So the answer is root 2. However, this does not, I guess a warning about this is, this only works for certain values of R. It works if R is between -1 and 1. Obviously, if R is 1, you can't divide by 0, and if R is 1, you have something like 1 plus 1 plus 1, or rather A plus A plus A, which obviously does not converge to a finite number. And similarly, if A is something like 2 and you have a sequence like this obviously you can't say it's equal to some finite number, it's infinite. So it only works for these values of R. But anyway, I hope this was interesting. And I think we'll stop there.